Okay, so in this video, I'm going to continue from this sequence of examples that I started in the previous two videos, and I will now go on to slightly more complicated functions. Here I'm going to do x to the 1/3. Start with that. So let's make a little table for this function for f values. So here I have a 0 at 0, and when x is negative, the function values are negative, and when x is positive, the function values are positive. And now if I calculate f prime, so let me put that over here, f prime of x is equal to 1/3 x to the minus 2/3. So here we have an important new thing happening. In particular, even though we didn't have any singular points, any singularities in the function, right? There was no blow-ups, there was no divide by zeros in the original function. All of a sudden we have one in f prime now. And it's at exactly the place where we had a 0 in f. Okay, so what does that mean? So x and f prime of x. So we still have to include, when we're looking at this f prime, we're looking for the sign of all intervals, the sign of f prime in all these intervals. And a 0 is not the only way the sign can change, right? At x equals 0 in this case, f prime is not defined, but it's possible that from one side of it to the other, we may have change of sign. And so let's see, I'm going to put sideways here, does not exist. Derivatives does not exist at that point. And so what happens when x is less than 0 and when x is greater than 0? So when x is less than 0, I'm going to rewrite this just because sometimes it's easier to think of these when you have the fraction, written in a more sort of transparent way, so I can see that it's in the denominator. Okay, so when x is negative, I'm going to plug it in here. I'm going to take you can think of x to the 2/3 as being either x to the 1/3 all squared, or you can think about it as x squared all to the 1/3. Whichever way you think about it, there's a squared in there, and you'll get rid of any minus signs. You can plug in negative values because a third in the fraction, that's a cube root, and that's fine. It's not like square root, which would not exist for negative numbers. So this is defined, and it's positive. And what about for x positive? Also positive, because there's that squared inside this function, right? The x gets squared at some point. Okay, so now already we can see that our critical point here, we had a critical point in, we had a singular point. So x equals 0 is a singular point. Some people call this a critical point, but I'm using singular to distinguish a 0 of the f prime as opposed to a point where it blows up. So x equals 0 is a singular point of f because its derivative does not exist there. And the sign here, look, it does not change sign. So f prime is not changing from one side to the other. So that tells us that, the function is defined, but the slope is blowing up, and what we have is a positive slope on one side and a positive slope on the other. So we know that we do not have a min or max here. Okay, we can't take a second derivative and see what the value of it ends up being because the second derivative is going to have the same problem. We can't evaluate it at the origin. So we have to look at concavity to find out anything else. Concavity on either side of the origin. So I'm going to get fx here and f double prime here and make a table for that one. And what is f double prime of x going to be? So here, I'm going to go back up to this form because it's easier for me to do the power rule. So I'm going to get negative 2 over 9, x to the negative, and when I subtract 1 from minus 2/3, I get minus 5/3. I'm subtracting 3 over 3. So again, we have at x equals 0, we have a does not exist in the function in f double prime, so the second derivative does not exist. But now we can see what happens on either side of it to determine the shape of the function. And in this case, we get that there's a negative number here, and for x negative, we plug in a negative value here. The cube root doesn't affect it, and the fifth power also doesn't affect the negative sign. So we end up with a negative times a negative is a positive. And on the other side of 0, here we get a negative multiplied by a positive, that's going to be negative. So f double prime, even though it does not exist, we know that the sign is opposite. And that tells us that we have a concave up function on the left and concave down on the right. And so graphing this, what does that mean? Well, okay, we have a 0 at 0. It's got to be concave down on this side. It's got to be concave up on this side. And the slope has to be positive throughout. So it's increasing and concave up to start with. Over here, increasing and concave up. And the slope has to get infinitely large. And it's infinitely large and positive because this function is always positive. The slope is always positive. Then it's got to go from infinite down to a finite positive slope and concave down. And so that's the shape of our function. Okay, so let's look at a very similar example. We have f of x equal x to the 2/3. And so how does this differ? So first of all, we have x and f of x doing similar things, except now there's a squared. So we have a 0 at 0, and we have to consider what happens when it's negative. When x is negative, f of x is positive because of that squared. And when it's positive, f of x is also positive. So now f prime of x is going to be 2 over 3x to the minus 1/3. So we still, because it's a fraction between 0 and 1, we're still going to get that singular point. So we have x and f prime of x. And now we still have a special point at the origin, but here it's a singular point, does not exist. And so when x is less than 0, now if we plug in negative numbers here, that's a positive number, a negative number to the 1/3 power, 1 over it. The negative is going to survive all that. So we end up with negative, and when x is positive, we end up with positive. And so that says that up here we find out that that f is going to touch the origin, but it's going to have been positive on either side. And then from this, we find out that it's got a negative slope on the left and a positive slope on the right. So just roughly, it's going to hit 0 at 0. It's got to come down from above, positive value, negative slope. And then here, it's going to be positive value, positive slope. But I've drawn this wrong intentionally because we don't have concavity information. So now I'm going to take f double prime of x, and that's going to be minus 2 over 9 x to the, oh, something happened funny there, did it? No, that's okay. X to the minus 4/3. And so we get our table for x and f double prime of x. And when we have, again, we have this singular point at the origin. And when x is negative, f double prime, if we plug in a negative number here, the 1/3 power doesn't change that, but the 4 does. It makes that positive. And so we have a negative multiplied by a positive, negative. And then on the other side, when x is positive, we have a negative value, and here we have a positive value, because x is positive, and so we still have negative. And so what that says is that we have a function that's concave down on one side of the origin, concave down on the other, and the slope, even though the value of the function doesn't blow up, the slope does blow up. And actually, how does it blow up? Well, the concavity blow up. How does the slope blow up? If we go back to this function here, if I plug in negative values really close to 0, so the limit of f prime of x as x goes to 0 from the negative side, that is going to be a negative number, less than 0. And we knew that from this part of the table, right? And then if we come from the positive side, it's going to be a positive number. So I guess we already had that in this picture above. So let's update that picture. Here's x. Here's f of x. And now instead of having straight lines coming into the origin, we can correct that because we now know concavity. It has to be concave down coming in, and the slope has to go infinite from the positive side, infinite positive, infinite negative slope. And then going out, we have an infinite positive slope and concave down. So we have a seagull. Okay, so that is a case or two cases where we have singular points where the slope blows up, but we still can do all the same analysis. And the big reminder here is we just have to be careful always to include not just zeros of our function and derivative, but also singular points of our function and derivative, right? These do not exist points because the concavity and the slope can change even though you have this do not exist point. All right, so that wraps up the examples I was going to cover, and I may do one more and include it later in the playlist.